to the practice video on surface integrals and inherently parametrized surfaces because you need to know how to parameterize surfaces in order to complete surface integrals. So let's get started with problem number 1. So number 1, we are going to find the following things. So we're going to find t sub u, tangent vector of u, t sub v, tangent vector of v, and the normal vector of u and v, of course. And we're also going to find the equation of the tangent plane. So we're also going to find equation of tangent plane, and then I'll just say at the point where u equals 1 and v equals 4. So in this question, we're going to be solving for 4 things, basically, but it's all good practice. So the given parameterization is g of u comma v equals the following. We're going to have 2u plus v, comma u minus 4v, comma 3u. Alright, so first off, we're going to find tangent vector of u. So that'll be taking the partial derivatives of each component with respect to u. So on the first one we have just a 2, second one we have a 1, and the last one we have a 3, right? And then t sub v, that one's going to be, oh, that is a weird v, hold on. T sub v, there we go. That's going to be taking the partial of each component with respect to v. So that'll be a 1 and a negative 4 and a 0, right? And the last one we don't even have a v component. There. Okay, so we found the first two. That was pretty easy, right? And now we'll find the normal vector, and that is found by crossing t sub u with t sub v, and then setting up the ijk thing. So we have an I, a j, and a k hat, and then we set up the first row by plugging in the t sub u stuff. So we have a 2, a 1, sorry, that's a 1, and this is a 3. And then the last row is t sub v, so that's 1, negative 4, and a 0. Alright, so now we're going to use the process. So we cross out everything here, and we just look at the little square here. So that'll be 0, 0, minus the other diagonal. So that's a minus 12, okay? And then we have a minus j hat, and that one's going to be, we're going to cross out everything here and focus on the outer ones. So that'll be a 0, because 0 times 2, minus the other diagonal, 3 times 1, which is 3, okay? And the last one, plus k hat. So that one, we're going to ignore everything here and everything there. So then we have a 2 and a negative 4. So that'll be a negative 8, minus the product of the other diagonal, which is a 1, all right? So what this is going to turn out to be is the normal vector is going to be a positive 12 and a positive 3 and a negative 9. Okay, so now we found the third one, the third part for our question. And now the last one is find the equation of the tangent plane at these points. U equals 1 and v equals 4. Okay, and we'll continue this on the next slide. So we just found that the normal is 12, 3, and negative 9, right? And our point is u equals 1 and v equals 4, okay? So what we need to do, our equation of a tangent plane, so the equation is given by, and you might have learned this in 32A if you've taken that class, but the equation of a tangent plane is given by x minus x naught, y minus y naught, and z minus z naught. And that is dotted with the normal vector, and this is supposed to equal 0. Okay, and this should give you the equation for a tangent plane. So we have our normal, so that's good, but we don't know, well, in our final formula, our x, y, and z, like the plain ones without the naught down here, those are still gonna be there for our equation. But what we need to solve is this one, x naught, a y naught, and a z naught. And the way you find that is just plugging in to find the point or plugging in u and v into our parameterization to find the x, y, and z values. So g of u and v, again, I'm going to reiterate here, was 2u plus v, comma, u minus 4v, and a 3u. So if we plug in a 1 and a 4, let's see what we get. So we have 2 times 1 plus 4, and then a 1 minus 4 times 4, and then a 3 times a 1. Okay, so this is going to turn out to be what? We have a 2 plus 4, so that's a 6, and then a 1 minus 16, so that's a negative 15, and then a 3. Okay, so this is, in effect, our x naught, our y naught, and our z naught. Okay, because these are these basically mean the value of the coordinates. So the coordinates at the point that we chose, which was 1, 4, and u and v coordinates. Okay. So anyways, you can ignore that arrow. Okay. So now we have that, and we're just going to plug them in and simplify. So we have, let's see, we're going to plug in, wait, let me write that a little bit down more. So x minus x naught, which is 6. And then we have a y minus y naught, which is negative 15. And a z minus z naught, which is a 3. And we're going to dot that with the normal vector. And the normal vector, which we calculated on the previous slide, which was 12, comma 3, comma negative 9. And this is supposed to equal 0. Okay? So now we just simplify here. This turns into positives, right? And then we're just going to dot this out. So that means multiplying the first components together. So that would be 12 times x minus 6. And then we're going to add it to the product of the second component. So that would be 3 times y plus 15. Okay? And then add it to the product of the third component. So that's a negative 9 times z minus 3. And that's going to equal 0. Okay? So now at this step, we're just going to continue simplifying. So we get 12x minus 72, and then a plus 3y plus 45, and then minus 9z, and then that turns into a plus 27, okay, and we have equals 0. So what these actually turn out to be is 12x plus 3y minus 9z, and I'm just going to move everything to the other side, the constants, So if we add the 72 over, and we're going to subtract the 45, and subtract the 27, and this side actually just turns out to be 0 anyways. It's not always going to work out like that for the equation of a plane. It might be like equals 5 or something, but that just happens to equal 0. So our final equation for the plane is 12x plus 3y minus 9z equals 0. So at this point, technically this is correct. That's fine. Or we could also just divide by 3 because we can on both sides, and it's not going to change the right side. So if we divide by 3, we just get 4x plus y minus 3z equals 0. And that is also just as correct. Just a little bit simpler, right? Okay, so that's it for that question. This is our equation of a plane. That was the fourth part that we had to answer. And now I have another question on a surface integral. So, number 2, this is going to be, so we're going to calculate the surface integral of a scalar function, some f of x, y, z, ds, using, we're given the following parametrization. So g of uv equals u cosine v, u sine v, and u. Alright, so you might or might not recognize this as the equation, or the parameterization for a cone, okay? And we're also given that the u ranges from 0 to 1, and so does the v. So pretty simple bounds here, so that's good. And we're also given a lot of given things. We need to be, right? Because if you don't have enough given, then you can't solve the problem. But so our given scalar function is z times x squared plus a y squared. Okay? So, again, the way we break it down is double integral over the domain. This is the domain of u and v in the uv plane, remember? And then we're going to calculate our scalar function, but this time in terms of u and v. Okay, so this is technically our x, our u cosine v, u sine v is our y, and our z is u. Okay, and then we have times the magnitude of our normal vector. Okay, and then du dv, of course. So let's get started on finding the normal vector. And we do that by finding the tangent vectors, right? The partial tangent vectors. So t sub u is going to equal the derivative, all of these components being derived with respect to u. So that would just be in the first one, that's cosine v, and then we have a sine v, and then a 1. Okay? And t sub v now, that's going to be a little bit more complicated. So then we have a negative u sine v, and then a u cosine v, and a 0, right? Because there's no v in the last component there. Okay, so now let's cross these, and we'll get our n. So n, normal vector of u and v, is equal to the cross product of t sub u and t sub v, and that's equal to, here's our I, j, and k. Alright, so then we have cosine v sine v, 1, and then negative u sine v, a u cosine v, and 0. Alright, so we're going to start with our I hat, so that's going to be 0 minus this diagonal here, so that's u cosine v. Alright, now we have minus a j times what? 0 again, multiplying these outer ones here, and then minus the product of this one and this one, which is a negative, so that'll turn into positive, u sine v. And our last component, that's going to be the longest, so k hat is going to be the product of these two, so u cosine squared v, minus the product of these two, which is a minus, so that'll turn into plus, u sine squared v. Okay, so that's a handful, but ultimately what we get for our normal vector, so our normal vector with respect to, of u and v, is the following. We have a negative u cosine v, and this here is a negative u sine v, and this last component, if you factor out a u, that's just going to be u, because cosine squared plus sine squared is just 1. Alright, so we found our normal vector. Now we have to normalize it, or find the magnitude. I'll do that on the next slide. So our magnitude is going to be equal to, that's going to equal to negative u cosine v quantity squared plus negative u sine v quantity squared plus u squared. Alright, and all of this under the square root symbol, and what we get is a u squared, and I'm just going to factor this out right away, cosine v plus sine v. That's what we get from the first two terms, plus another u squared. Okay, so this should look similar from, well, maybe not if you didn't watch the previous example, or previous concept videos. But anyways, this happened before where we had something like this, and this is basically going to be 1, right? So that'll be a u squared plus a u squared, so that is square root of 2u squared, and this is square root of 2 times u. Alright? So now we found the magnitude of our normal vector, and now I think, so that was the first thing, first component, and now we should find the scalar function, but now in terms of u and v. Okay, so that's going to be, it was, alright, so f of x, y, z, it was z times x squared plus y squared, alright, but now our z is u, and our x is now a u, sorry, do that all the way over there, it's a u cosine v, so that's squared, because that goes in the x spot, this is our x, this is our z, and then our y is u sine v, and that's squared as well. So this is our y. Alright? So now let's simplify this and see what we get. Okay, so we have a u times u squared cosine squared v plus u squared sine squared v, And here you can see we can factor out the u squared, so we get u times u squared times cosine squared v plus sine squared v. And again, the trig identity comes in handy, and that's just 1. So our f of g of u and v is equal to simply u to the third. All right? So now we can plug everything in because we know we have all of our tools to use. So we know that these are the given bounds on u and v. They're the same, 0 to 1. Okay? We have the magnitude of our normal. Oh, no, sorry, I underlined the wrong thing. Just kidding. We have the magnitude of our normal vector here. We have our scalar function in terms of u and v, and we can start. So we have 0 to 1, and then 0 to 1 again. It doesn't matter which order in this case because they're the same bounds. But then we have our u to the third, and then times square root of 2 times u, and then I'll just write du dv. Okay? So now we just simplify and solve. So we get 0 to 1, 0 to 1, and I'll write the little square root of 2 in front here so we don't have to bother with it. And then we get u to the fourth, and then du dv. And here, this is iterated. I was going to say integrated. It is iterated integral. So we can break it up and group them into separate integrals. So that'll be 0 to 1, and I guess I'll just do the dv's first, or the v stuff. And that's just a 1. And then we also have the u stuff, so that's u to the fourth, and then a du. So this is equal to square root of 2, and then we have v as v goes from 0 up to 1. And then we have a 1 over 5 u to the fifth as u goes from, I'll just write it inside the parenthesis, as u goes from 0 to 1 as well. I wonder if I can squish this in. But anyways, so the point here is that we have square root of 2. Okay, no, I'm not going to squish this in. I'll let you guys see it very spaciously. Okay, so then we get, what do we get? Square root of 2, and then 1 minus 0, and then a 1/5 times 1 to the fifth minus 0 to the fifth. And so this is a 1, and that's a 1/5, and that's a 1. So our final answer, and I know I'm taking up the entire slide for this, is going to be square root of 2 over 5. Okay, so that is the surface integral with the given scalar function and the given bounds and the given parametrization. Okay, so that's it for the practice. And again, good luck on your homework. And I'll talk to you in another video if you watch.